Okay, thanks for the nice opportunity. As mentioned, I'm Paul Muñoz from the Freie University of Brussels. And today I want to show how we develop some AI-based applications for water management and also for real-time applications. So you will see that this is relevant in data-scarce regions where traditional monitoring and modeling often falls short. So this talk is on the context of the WEFE Nexus. So in South America, this is emerging. I mean, this is critical. We are witnessing how the climate crisis, how the water crisis is changing the lives of 500 million inhabitants in the region, and how this is becoming more challenging with climate change. And this affects the most vulnerable communities, but not only the communities, but also entire sectors, such as the power sector and the food sector. So for the power sector in particular, this is also due to the fact that there is a dangerous dependence on hydropower in the countries in South America. So on average, the dependence is about 60%, but in Ecuador, in countries such as Ecuador, this dependence can be as high as 80%, which makes the country vulnerable to these climate variabilities and change. But to be more specific, the power crisis in Ecuador started in 2023. And after the long drought in the region, we experienced water depletions in the main reservoirs of the country. And we had power cuts for up to 13 hours in a day, affecting all that you can imagine. But somewhat counterintuitively, not only droughts are affecting the power crisis, but also heavy rains, because they produce sedimentation, they produce erosion that also forces the shutdown of these hydropower facilities. So these both extremes are affecting, and there's the need to face this. So today I want to showcase an exemplary case study, a hydropower project in southern Ecuador, in which we have developed a number of AI-based applications. So this basin is important for some reasons, some characteristics you can see in the screen. Yeah, it is in the southern part of Ecuador, draining to the Pacific Ocean. But in the outlet of the catchment, there is the power dam, one of the main power dams in the country. It started operations in 2018. The precipitation runoff response is in the order of hours. So it means that if we want to develop a forecasting system, it has to account for the dynamic in the hourly time step. To make it more challenging, there's no single rain gauge in the area. So we have to rely on satellite precipitation estimates. So what we first did is that we looked at several precipitation satellite sources, and we found out that we cannot rely on a single one. So we made this simple exercise. We looked at two different extreme hydrological events, and we saw that for one product, we found a corresponding signal for precipitation, and then for the other product, we didn't get anything. And the opposite happened for another event. So this means that we cannot rely on a single satellite precipitation source. So this, together with the fact that we only had 4 years of data for training and testing the models, and together with the fact that we had to produce models that run fast and implemented in servers, we decided to go for this decision tree-based algorithm, the random forest, to produce this forecasting system, hourly forecasting system for the next 16 hours. And this was done with a number of modules. Perhaps the most important one is the communication module. This means that we produce a forecast and send the updated forecast for 16 hours to dam operators so they can manage the plants, so they can schedule how much energy they will produce in the coming days. And this is running since 2021. That's a mistake in the screen. This system is running since 21, and it hasn't stopped. And this system is recalibrated every 6 months with more data added to the model. Just to give you some example, this is how the performance of the forecasting system looks like. And if we zoom into the 7-hour lead time case, you can see that we can forecast runoff cubic meters per second up to 200, where the mean runoff is about 50 cubic meters per second. So you can see that there's a nice fit between observations and forecasts. For the peak flows, you can see that in the case of the green box, we can also reach the peaks, but in other cases, such as in the yellow box, we overestimate runoff values. So there's the need for specialized forecasting based on focus on peak flows. But a question that we always get is, how do we know what is happening inside the box? So there's the need to enlighten the black box, and this can be done in 2 approaches. The first one is by looking at the architecture of the AI, and the second approach is by helping AI models to assimilate the information. So we went for the second approach, and we added physical knowledge into these deep learning neural networks. And what we did was to use static data, information on soils, land use, land cover, topography, and integrate this information together with LSTM, which is for time series and sequences type of data. So we proved that by combining this information, we got better closure of hydrological balance, better performance for peak flows, but not only the peak flows, but also the time to the peak flows. So this proved to be also effective, and this is now implemented in this forecasting system that it is operating since, I told you, 21. Something else we did was to look for another approach to better exploit satellite estimates, and what we did was to employ object-based algorithms to extract key predictors to the models. So in summary, what we did was to track down storms that produced peak flows, both in space and time, and then we derived new estimators for these extreme events, and then we found out that we can indeed outperform the performance of traditional or only black box AI models. So you can see in the blue dots, we got a better fit when compared to these referential models, which didn't account for this static data coming from process-based knowledge. We also found that the most difficult events to forecast are the ones in which we have spatial extensive storms across durations of short and long durations. And this also serves to know how to move forward with these specialized models. So if you are using satellite data for real-time applications, you know that you have to deal with data latency issues. This means the times it takes from the satellite scan till you get the information in your laptop for running the models. So this, in the case of this satellite source, IMER-ER from GPN mission of NASA, is about 4 hours. This means that if I access now to the latest precipitation information, that will be the information of 4 hours in the past. So this has direct implications in early warning systems and operational forecasting systems. So we trained another deep learning model, one accounting for spatial patterns, convolutional neural networks. And what we did was to eliminate this latency gap by predicting these satellite images, global satellite images using these networks. We found good results. Now this is promising for airway systems and also to extend the lead time of these short-term forecasting systems. Of course, there are some limitations according to the spatial and temporal scales that you want to predict, but this is a step forward in this direction. And just to finalize, I want to state 3 key points. The first one, as it was mentioned, we are only scratching the surface. We're mostly going into machine learning, deep learning, but there's also robotics, there's digital vision, there's natural language processing. So we now have to look in this direction as well. South America and the Global South is underrepresented in most global models because we don't have many data in these regions. So there's the opportunity for AI to now use and fuse emerging data sets and also data collected by citizens to now have more representation and now have more climate impact analysis that are more meaningful to our context. And finally, I also want to highlight this flagship initiative of UNESCO, the CRIDA, and AI also gives opportunities to get more value from the data. Sometimes this approach cannot be implemented because there's no data. Now we can use AI to get more information from data. This is from my side. Thank you very much.